Welcome back, everyone, to another explainer. I am so thrilled you're here. Today, we're taking a fascinating look at the absolute foundation of all programming. Whether you're building a simple little calculator app or the next massive social media platform, everything starts right here with variables and data types. But instead of getting bogged down in dense computer science jargon right out of the gate, we're going to look at this through a really relatable, everyday analogy: your kitchen. So picture this. Have you ever actually looked inside your kitchen cupboards and really thought about how things are organized in there? Imagine if you just threw all your groceries, your rice, your sugar, your lentils, your milk, straight into one giant pile on the floor. It would be an absolute disaster, right? When you want to cook, you need specific ingredients and you need to know exactly where to find them. That's why we use storage boxes and jars and containers. Well, in the programming world, your computer faces that exact same organizational challenge. It has to manage a massive amount of information to run a program, and to do that effectively, it needs its own digital containers. There's a quote from our source material that really hits the nail on the head here. It says, "Variables are like containers in a kitchen that hold dal, rice, milk, or water. You can empty a container and put something new in it." Building a program is essentially just like following a master recipe. You absolutely need distinct containers to hold your raw ingredients, which, in this case, is your data. Throughout the execution of your code, you'll be reaching into these containers, checking what's inside, maybe mixing a few together or swapping out an old ingredient for a fresh one.
Section 1, Memory Addresses and Labels.
So inside your computer, the digital kitchen, where all the immediate active cooking happens, is the memory, what we usually call RAM. But how exactly do we set up our containers in there? Well, a variable is basically just a human-readable label, or identifier, for a specific memory location in a computer's RAM where your data is stored. Actually, scratch that. Think of it less like a digital location and more like just taking a blank piece of masking tape, writing a name on it with a Sharpie, and slapping it onto a blank storage box. Without that label, you just have thousands of identical, anonymous boxes. The variable gives you, the programmer, a simple, recognizable way to ask the computer to retrieve or store information later on. There is a huge contrast between how a computer thinks and how we think. A computer actually identifies a location in its memory using these complex, intimidating hexadecimal addresses, like 0x75FF, 5FABBFF5A8. Can you imagine trying to write a recipe or a program where you had to memorize thousands of those numbers just to find your data? No way. It'd be nearly impossible. By simply naming that exact same location, price, we completely bridge the gap between machine logic and human understanding. Variables do the heavy lifting of remembering those terrifying memory addresses, so you literally don't have to. Section 2, Exploring Core Data Types. Okay, so we know how to label our boxes now, but what about the ingredients themselves? Just like you wouldn't pour liquid milk into a fragile paper bag or store sharp knives in a flimsy plastic Ziploc, in coding, the container's rules have to match the item inside. Let's demystify the 3 core data types you're going to encounter in almost every single programming language. First up, we have the integer. This is used for whole numbers, like someone's age or a quantity of items. Our code example here is just the number 24. Next, we have the string. A string is basically a collection of characters, used for text. Whether it's a single letter or a full name like Tony Stark, you use a string, and it's usually wrapped in quotation marks so the computer knows, hey, I'm reading text here, not a code command. And finally, we have the Boolean. Think of a Boolean as a simple light switch. It only has 2 states, true or false. This is incredibly useful for conditional logic. Like, checking if a user is logged into a website. True, they are. False, they aren't. Section 3, Changing Values on the Fly. Now that we've got our data neatly sorted, we need to talk about why these containers are called variables in the first place. I mean, the root of the word literally means having the ability to vary or change. A program is a living, breathing set of instructions that operates in real time. Let's walk through how this works step by step. Imagine you're writing code to track a user's birthday. In step 1, you create a variable box, label it age, and assign it the integer value of 24. Awesome. Now a whole year passes in the program's life cycle, and boom, the user has a birthday. To update this, we don't need to go find a brand new box. In step 2, the program just effectively empties the current contents of our age box. Then in step 3, we simply reassign the box with a new integer, 25. The label on the outside stays exactly the same, but the ingredient inside has varied. And that right there is what makes software so incredibly dynamic. Section 4, Preventing Type Mismatch Crashes. But as you can probably guess, this power to mix and match ingredients comes with some danger. Just as a master chef knows you can't substitute salt for sugar just because they look kind of similar, a programmer has to know how different data types interact. I want you to think about this logically for a second. What happens if we try to mathematically add the integer 123 to the text string Harry? If you say 123 plus Harry, it makes absolutely zero sense to the human brain. But how does the computer's brain react to that instruction?
Boom, runtime error. The whole thing crashes. The machine is incredibly obedient, right? It tries to perform the mathematical operation you asked for. But when it looks inside the first box and finds a number, and then looks inside the second box and finds a word, it simply doesn't know how to do arithmetic on text. It literally just throws its hands up and yells, "Type mismatch."
So the absolutely crucial takeaway here is that data types aren't just there to be annoying rules. They are vital safety features designed to protect your code from breaking. When you do inevitably run into these errors, here are the troubleshooting best practices you're going to want to follow. First, just remember that data types exist specifically to prevent those invalid operations. Always validate your variable types before you try to do math. If you realize one of your boxes accidentally holds the text string version of a number, say a user typed 123 into a text box, you have to use your programming language's tools to convert that string into a usable integer before you can add it. And finally, if you ever lose track of what's in your containers, use built-in type-checking functions. Languages like Python and JavaScript have these, and they let you essentially peek inside and inspect those unknown boxes before you try cooking with them. Wow, we have covered a lot of ground today. From setting up our digital kitchen with labels to making sure we aren't trying to do math on the word Harry. Understanding variables and data types really is the absolute key to unlocking everything else in software development. At the end of the day, it's all just organizing containers and manipulating what's inside them. So I'll leave you with this. If you can master labeling your boxes and carefully checking your ingredients, what incredible digital recipes are you going to code next? Thanks so much for joining me on this explainer, and happy coding.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are